Hello and welcome to section 9.1. In this video we'll be going over the equations needed to find centers of gravity, centers of mass, and centroids. So if you don't remember, that's basically where does the object balance. That's what we're looking for. Alright, so we'll start off by reviewing an equation we've already looked at. So if you remember back with our rigid bodies, we had an equation to find distance. So we noted that distance was equal to we had this equation, distance equals moments divided by force. This was when we were doing resultant forces and resultant moments, and we could replace a system with a force and a distance. If we rewrote this, we could say that it is, well, what if we said it was the sum of forces over the sum of moments over sum of forces? Then we could rewrite this as the sum of the forces times each piece of distance, so we'll put a tilde on that, over the sum of the forces. So all of the forces, and then for each force, find its individual distance. And then, so basically I have a weighted piece up here and an unweighted piece down here, and what will pop out is just the overall distance. So we're going to follow this pattern as we go through. So you might remember some of this from geometry. So for center of gravity, so this is where we say the weight is acting whenever we do our free body diagram. We get the equation. So I'm only going to do these in the x. I'll do one in the y just so you can see how they change, but in general I'm just going to only write these equations for the x. So again, we're going to try to find the distance in the x direction. And so we're going to accumulate all of the weight of the body, and then for each individual piece of weight, we're going to find its center of gravity in the x direction. We can also do this in the y. And the equation looks the same, we just sub out. Now our strategy is, if you go and find integral d weight, don't go re-find it over here, it's the same number. Now if we don't want to go through and find the entire weight, maybe we have a problem where gravity is constant, which is going to be most cases. So if g is constant, so we're like near Earth or something, so we can assume the gravitational field isn't changing, then our center of gravity, so our CG, will be equal to our center of mass. So, how do we find the center of mass? We do that. Looks the same. X bar, integral the location of the x bar for each piece of mass, divided by integral d mass. And again, y will look the same. And then if rho is constant, or rho is density, then the center of mass will be equal to the centroid of a volume. And also other shapes, but there's some other things we have to do. So centroids. So if you can make these assumptions, then you can kind of go down and you can find the simplest version. So for a volume, x bar integral x tilde d volume divided by integral d volume. Oh, and I should note that d mass is equal to rho dv, just like d weight is equal to g dm. So this strategy of taking this piece and breaking it up into something that's constant and something that's differentiable is something you're going to see throughout. If I have an area instead, so the area can also be where the center of mass is if the area has constant thickness. Or if I kind of have some kind of a shape that's uniform about an axis, I can also just use areas as well. So you'll see that in example 2. So this is just x tilde d area, and then the last one is the simplest one, which is a line. And so there's some things that are modeled with like wires or whatnot. And so the pattern is just the same thing all the way down. It's just accumulate the entire length, the entire area, or the entire volume, and then for each individual piece, figure out where its centroid is, or figure out where its center of mass is, or figure out where its center of gravity is, and then do your division. And if you have a y direction or a z direction, the equations look the same. All right. So if you have any questions, feel free to reach out.